I'm Richard Hollingham, and this time for the Planet Earth podcast, I'm in Scotland to contemplate coral. We'll also be meeting an air detective hunting down new greenhouse gases and studying the meteorite strike, blamed for the dinosaurs' demise.
In that moment of explosion, it's like about 10,000 times all the nuclear warheads in existence all going off at once.
I want you to picture a coral reef. You're probably thinking of a warm blue tropical sea teeming with multicoloured fish. Well, let me shatter that calming image for you, because the coral scientists here at Heriot-Watt University in Edinburgh are studying is in the rather colder and altogether less hospitable waters off the west coast of Scotland. Well, with me just outside the cold room, which is essentially a big fridge. In the corridor at Heriot-Watt are Murray Roberts and Laura Wicks from the Centre for Marine Biodiversity and Biotechnology. Now let's go inside and have a look at some of this coral here. Through the door and into, well, it is a cold room. Murray, what sort of temperature is it in here?
So in here it's about 7 degrees centigrade. So what we're doing is mimicking the temperatures that these corals live at. And like you say, corals, we think immediately of tropical waters, maybe about 27 degrees centigrade. So it's obviously a bit different. We've put our fleeces on to get in here. And inside we've got a whole series of experiments that you can see around us. And these are all individually replicated experiments that allow us to put the corals in the environmental conditions that they will experience in about 100 years' time.
Well, we'll come on to that in a moment, but let me just describe what's here. It's really benches covered in buckets with lids, almost like paint pots.
Basically, that's right. So, benthic ecologists, people like us that work on deep-sea corals, use buckets for almost everything. And here we're using the buckets simply as little aquarium tanks to keep the live corals in. So if we have a look in this one here...
So this is on a bench with about, 12 buckets on it?
That's right.
Here?
We've got 4 buckets together. We lift the lid off, and inside you can see the individual corals, and we prepared those by taking them off one of the big colonies and making a fragment, and then sticking it into an aquarium putty, into a heavy base that allows it to sit like that. So we can then put food into the water and allow these pumps to circulate the water around these little buckets to keep them in a really nice environment, actually.
Now, let's look in here then. You've got 4 in here. Now, they're not multicoloured like perhaps you get in a tropical sea. They're whiter or almost bleached, but clearly not dead. There seems to be some movement. If you look very closely
right.
to the tips of them.
You can see the tips of the branches there have tentacles sticking out, and the tentacles are a lot like sea anemones, and in fact sea anemones and corals are really closely related. You can think of the corals as sea anemones with skeletons. Those skeletons, though, over time grow up and can form huge reef structures, and the fascinating thing is that they do that even in the deep sea. And that was the big surprise for us all about 10, 20 years ago, when people began to realise the scale of these reefs and how widespread they were all around the world.
So where did these come from? So I said off the west coast of Scotland, they're called cold water corals, very cold water. Where are these from then?
These ones are actually from the west coast. They're from off the island of Mingulay, which is in the Outer Hebrides. It's at the southern end of that island arc of Atlantic islands. And these corals were sampled there last year from the research ship Discovery as part of this project. What we've done is bring them back, and now we're looking at their response to, in this experiment that Laura will tell us about in a minute.
Okay, Laura, great opportunity to bring you in. I mean, you're about to set off on another scientific investigation on the ship, and you're looking at what?
What we're looking at is ocean acidification. So it's predicted in the future that because of the carbon dioxide in the atmosphere, the oceans are actually becoming more acidic. So previously, for the past few million years, the oceans have been at 8.2 pH units. It's thought by the end of the century they'll go down to 7.9, and we want to see how these corals and all the other animals associated with them are going to respond. Will they still be there in 100 years?
So these look incredibly fragile, but how much can they cope with in terms of change?
Well, that's what we don't know, really. We've only started doing work on cold water corals, like Murray said, in the past 10 years. There have only been a few experiments in the laboratory. We obviously can't do experiments out at sea because these corals are in 130 metres of water. Some of them go down to thousands of metres. You can't just do an experiment out there like you would on a tropical reef. Our initial experiments that we started last year are showing that corals may actually be able to adapt to changes in their pH, but we also don't know how they respond to changes in their temperature, and having these two stressors together, initial results are showing that things aren't looking that great for them.
Murray, how important are these coral reefs? I mean, these, even though they're not the multicoloured coral, are still beautiful to look at. Their twig-like structure and the little tentacles at the top. But are they important?
They are important for a whole variety of reasons. Some of them we're only just beginning to understand, but there's a few basic facts that are really, really surprising. So now, in the last few years, we've come to realise there are actually more species of corals, when you look at the whole group in the deep sea, than there are on shallow tropical reefs. If you take the entire variety of corals that there are on Earth and you look at the numbers, they're in fact more deeper than 50 metres than there are shallower than 50 metres. This is just extraordinary. Nobody really appreciated that. No one also appreciated how good these things are at making habitat. Because you have to go there and see, and it's only in the last 20 years that technology has allowed people to develop submersibles or to create remotely operated vehicles to see these things. When you go and you see them, you realise that they form groves, extensive reef complexes of corals that have grown up. The Mingulay reefs have grown up over the last 5,000 to 6,000 years. The reefs off Norway, they've been dated back 11,000 years. The mounds that we're looking at in international waters just beyond the Irish economic zone, they trace their histories back 2 million years before present.
So what would happen if they weren't there? What would happen to you? Get a collapse in the whole ecosystem, affecting fish stocks and everything else?
Basically, these are engineers. These little corals, making their skeletons, are engineering a habitat. That structure traps sediments and grows up to form a reef. That reef, in turn, is providing home to literally thousands of other species. It's mostly things that like to feed from the water column, like the corals do, things like sponges and sea mats, and hydroids. These all live in huge abundance and diversity on these reefs. That alone is valuable. I mean, we don't know the value of that diversity in economic terms till we start to understand it. And it's interesting to note that some of the most potent anti-cancer compounds now in development have come from deep-sea sponges.
Now, Laura, I should say you're not actually going to be jumping in the water. You're using remotely operated submersibles, ROVs, remotely operated vehicles.
Yep, we have the Holland One coming with us from Ireland, and we basically send this vehicle down, and it's like a big robot. It's got mechanical arms, and we'll watch on the video cameras, and we'll be able to select corals and animals from the reefs to bring back up for us to do experiments on.
Murray, it strikes me you're only just starting to understand and appreciate these animals, because they are animals, aren't they?
That's right,
Coral.
they are.
And yet they're already under threat.
Well, this is one of the huge ironies, and they're under threat from several sources. In the last decade, 20 years or so, it's become really apparent that these corals have been substantially damaged by deep-sea trawling, where nets are dragged across the seafloor and run over coral beds. They're flattened, actually, very, very, very quickly. Huge concern has been raised about that, and marine protected areas have been created to help conserve these corals. Now, the ultimate irony seems to be that our addiction to fossil fuel use and the change in the carbonate chemistry of the seas is making the very environments that these corals have lived in for thousands of years inhospitable. And that's one of the drivers for our science, is if the predictions of the modelers are correct, the seas that these corals are growing in could become corrosive to their skeletons within 100 years.
Murray Roberts and Laura Wicks, thank you both very much. And Laura will be recording audio diaries for us, which you'll hear in the coming weeks and months here on the Planet Earth podcast. And we'll stick some pictures of the room here on our Facebook pages. You can also follow the Planet Earth podcast on Twitter. Just search for Planet Earth Online. There are several theories as to why the dinosaurs became extinct. The most popular is that they died out as a result of a huge meteorite, some 10 to 15 metres across, landing in Mexico. It created what is known as the Chicxulub crater, one of the largest impact structures known on Earth. But although it was formed millions of years ago, we know surprisingly little about it. Well, now, Earth scientist Penny Barton from the University of Cambridge's Bullard Laboratories is exploring the geology of the crater. Sue Nelson asked her to describe what happened when the meteorite hit.
Something that big, when it hits the surface of the Earth, the outer part of it is still out in the outer atmosphere. And so the front of it then slows down hugely, and it becomes a gigantic sort of smarty shape and becomes hugely overcompressed before it explodes dramatically and creates a huge amount of radiation. So that in that moment of explosion, it's like about 10,000 times all the nuclear warheads in existence all going off at once.
That's almost unfathomable, isn't it?
It's very hard to imagine, yes. And to give you an example, if that was to happen, say, in northern Britain today, just simply the radiation from the initial explosion would kill everybody in France, Germany, Denmark, Norway, Sweden, Britain, northern Spain, Iceland, just in that initial blast.
Now, you're specifically interested in the crater in Mexico. Give me an idea of its size and what we know about its construction.
Its diameter is about 100 kilometres, but the total area affected is more like 200 kilometres. And it's buried completely as it was formed beneath about a kilometre of subsequent sediments. So they're like a paving slab stuck down on top of it that has kept it pristine in condition. There are 2 other craters of this kind of size known on Earth, and both of those have been quite badly eroded away, so we haven't got them complete. So Chicxulub is unique because it's completely present, but because it is stuck away underneath these subsequent sediments, the only way we can investigate it is using geophysical methods.
That's quite interesting because I think most people assume that the bottom of the crater is the bottom of the crater, but what you're saying is it's not, because it happened so long ago. It's actually a kilometre underground.
That's exactly true. If you go to the Yucatan now, which is where this crater is, you won't see anything. There is no crater because it's completely filled in. But the crater, which is underneath this kilometre of sediments, is also much shallower than the crater which formed at the moment of impact. When the impact happened, there would have been a hole probably up to 30 kilometres deep, which is, again, is much deeper than any other hole we have in the surface of the Earth at the moment. You know, the Marianas Trench is, 8 kilometres or so. And about half of that depth is through material being thrown out or vaporised by the impact, and half of it is being compressed by the impact itself. So that compression then very quickly decompresses, causing the centre of the crater to come up. Just like when you drop a lump of sugar into a cup of tea, you get that drop coming up. And so within literally 2 minutes of the impact, this central part has rebounded, and the sides, which were thrown up to the height of the Himalayas just for a couple of minutes, then slide downwards and inwards, forming a much wider and shallower crater.
So what geophysical methods then do you use in order to examine something that's a kilometre underground?
The best geophysical method for imaging under the ground is using seismic waves, which are basically sound waves transmitted through the rock. And so the whole technique is very similar to medical methods using ultrasound scanning, and that travels down through the layers of rock and is reflected back from the different layers, which all have slightly different speeds of sound in them.
Because they're made of different materials.
Exactly, because they're made of different materials.
And what materials have you found at the level of the crater itself?
Well, the very top part is made of a mixture of pulverised rock from deeper down, we think, but of course measuring the speed of sound doesn't actually give you a label of what exactly the rock type is, and this is where we need some confirmation from actually drilling down at some point. What appears to be pulverised rock from deeper down has come up into a kind of ring shape inside the centre of the crater to form a characteristic thing called a peak ring, which is seen on other planets. In the centre of this peak ring, we see a pool of what we think was molten rock formed at the moment of impact, which is collected as a sheet in the centre, perhaps between 500 and 2 metres and 2 kilometres thick, which then solidified. And then on top of that would come the tsunami created by the gap. At the moment of impact, the sea would have been pushed out of the way, as well as the atmosphere, and then that would have whooshed back, bringing in a lot of sediments and so on top of this pool. And of course, this pool of rock was molten, and so wet sediments coming in top would have created all sorts of explosions and things going on, and there would have been a very dramatic, quite localised area where there were repeated tsunamis and explosions and a lot of disrupted sediments there, so it's quite hard to see what's going on.
Now, there are craters around the Earth that are in more accessible positions. I know you said that some are eroded, but we've also got craters on the Moon, and man has been to the Moon, studied lunar geology to a certain extent, used orbiters to study craters, formations on other planets in our solar system. Why do you need to examine this one?
Well, the key thing about being able to look at craters on Earth is that we can look underneath the surface of the crater into the deeper structure. And so we can understand the size and extent of the melt sheet, the properties of this peak ring I've been talking about, which is characteristic of the bigger craters, and begin to understand more about the cratering process, which just allows us to calibrate models that predict what happens in big meteorite impacts on Earth and on other planets.
Will it tell us more about the formation of our own planet?
Indeed, cratering was very important in the early formation of Earth, as it was on other planets. And also, it's important for us to understand the environmental effects of such an impact. These models can then predict the environmental effects much, much more clearly. And so that's important, both for looking back in the history of the Earth and looking forward to what might happen in the future, both for the Earth and for other planets.
Penny Barton. Site surveys at the Chicxulub crater are planned to start next year, and drilling will take place from 2014 onwards. If carbon dioxide and methane weren't enough to worry about, it seems we're managing to make a whole load of new greenhouse gases. By analysing air samples taken from high in the atmosphere, a team including Johannes Laub at the University of East Anglia has identified several new man-made compounds that are contributing to global warming. These halogenated compounds, a bit like the CFCs that are now banned, are only found in tiny concentrations, but their chemistry means they're likely to stick around for hundreds, if not thousands of years. I went to meet Johannes in his basement laboratory.
Basically, I have to reach up a bit. So these are air samples from Tasmania, and it's a man-made archive which goes back to 1978.
This cylindrical metal flask is among dozens hanging from the shelves that line the lab. Air inside these containers is reckoned to be some of the cleanest on the planet.
If you get very clean air from Tasmania, which is actually circulated across the globe basically, has gone to Antarctica and back again to Cape Grim in Tasmania, then you get a representative picture of what the compound is doing on a long-term basis in the atmosphere.
The samples are studied using a machine at the centre of the room which resembles an oversized photocopier. This mass spectrometer is able to separate and analyse air samples to identify minute concentrations of gases, to find chemicals that shouldn't naturally be there.
We're separating very small amounts of trace gases in the air from the main parts of it, which are oxygen and nitrogen mainly. And then we still have quite a mixture of different compounds. We have to separate them from each other. When we've done that, we actually destroy them. By destroying them, we can see a characteristic pattern, and that pattern changes over time and gives us the information which compound is coming through and how much.
So you're analysing these air samples, seeing what's in them, ignoring the big stuff, because we know there's going to be oxygen, we know there's going to be nitrogen in them. What are you interested in looking for then?
I'm mainly interested in halogenated gases because some of them have very long atmospheric lifetimes. So once released, it takes decades and sometimes centuries or even thousands of years for the atmosphere to break them down again. And these gases, especially the ones with the long lifetimes, very often very strong greenhouse gases. So they are actually thousands of times more effective than carbon dioxide.
Now, you've been called an atmospheric detective, and that's because you're finding these chemicals for the first time in the atmosphere.
Oh yes, there's lots of them, because industry is introducing more and more new chemicals. It's very hard for scientists to keep pace. In addition, our ability to find them has improved significantly. So we actually, especially with that system here, so we can actually find parts per quadrillion in the atmosphere.
So parts per quadrillion?
Yes.
But when you've got that tiny, tiny concentration of these gases, does it matter if they're greenhouse gases?
Well, for instance, we've recently detected new perfluorocarbons in the atmospheres. Well, their abundances are on the order of just below parts per trillion. But that means, if you sort of just do a quick calculation, that means several thousand tons of these molecules have been released in the atmosphere already. And in addition, they're very long-lived. They won't go away for the next several thousand years. Once added into the atmosphere, they become a permanent part of it.
Johannes Laub at the University of East Anglia. And Johannes has written a feature on his work, which you can find in the features section of Planet Earth Online. There's also a great picture there of the air sampling device he uses, which looks almost alien in origin. We'll put some pictures of his unusual looking lab as well on our Facebook page. And that's the Planet Earth podcast from the Natural Environment Research Council. I'm Richard Hollingham from Heriot-Watt University in Edinburgh. Thanks for listening.